Hi everyone, I'm Yash and in this talk I will be presenting learnings and analysis from TextVQA 2021 challenge. This work is joint collaboration with Amanpreet Singh, Devi Parekh and Marcus Rohrbatch from Facebook AI Research. The outline of my talk will be as follows. First, we will start with the description of the TextVQA dataset and introduce the problem statement. Second, we will discuss the top two baseline models from previous year's challenge. Third, we will announce this year's winners, and finally, we will conclude with an analysis of their submissions. TextVQA task requires an AI agent to answer a question by reasoning about the text in an image. For example, consider this image with a bunch of OCR tokens shown. A corresponding question asks, who is the author of the book on the top of the stack? To answer such a question, the VQA model has to reason about three things. First, whether the question is about the text. Majority of questions in the TextVQA dataset fall under this category. Second, it has to look at the relevant text among the other clutter that's present. Third, and finally, the model has to decide if the answer can be generated by weaving words from detected OCR tokens, or does it also require some additional vocabulary. TextVQA dataset was collected by annotating 28,000 images from the Open Images dataset with questions. During annotation, it was verified that every image contained at least some text, so 100% of the images contained text. After annotation, we ended up with 45,000 questions and their corresponding answers. Nearly 40% of these questions require reading text in an image, which is usually done via an OCR system. It was also found that nearly 14% of the questions contain spatial references such as right, left, above, below, and so on. Now let's quickly walk through some of the challenges in the TextVQA task. Open-ended vocabulary. TextVQA models need to have an open-ended and dynamic vocabulary which could be built up from the OCR token detected. These models need to be capable of weaving together the relevant OCR tokens to form a coherent answer. For example, on the right, to answer the question who wrote this book, the model has to select right tokens and arrange them correctly in the specified order. The text detector plays an important role as well. If the OCR tokens needed for answering the question are not detected, then it becomes unlikely that the model will be able to answer such a question. In the right image, we can see that the OCR token 18 is not detected, which is actually the answer, and hence the model fails on this. The models also have to account for spelling mistakes made during extracting the text. For example, you can see here in the image that an inverted logo of Crayola is actually parsed in a different language than English, and this is a failure at the point of text extractor. Some of the questions in the dataset require reasoning on top of the extracted text. For example, in this image shown, the model has to understand that it has to count all the different 10 pence coins it sees to give the final answer of 100. Finally, some questions in the task also requires understanding of world knowledge. In this example, to answer the question, what processor band is featured, model has to understand what a processor means. Now let's discuss the baselines of this year's challenge. First is the 2020 TextVQA challenge winner SMA model. We will be comparing this model with this year's challenge winners. This model had scored an accuracy of 45.51%. Our second baseline is the SAM or SAM4C model. This model was the runners-up in the 2020 challenge with test accuracy of 44.80%. Let's briefly compare these two models. Both the models have dynamic vocabulary created from detected OCR tokens. To generate their answers, both of them use a pointer network plus a generator. SAM uses Google OCR while the SMA model uses SBT Trans OCR. M4C uses a spatial graph guided attention within the transformer, while SMA solution uses a graph attention module. SAM uses spatial graph guided attention within the transformer, whereas SMA solution uses graph attention module. They both encode world knowledge just from the priors in the dataset. SAM had an accuracy of 44.80% and SMA had an accuracy of 45.51%. Now let's talk about this year's TextVQA challenge. First of all, a shout out to Evalia team for helping us organize and host TextVQA challenge on their platform and their continued support throughout the timeline. This year, we had 33 teams which participated and we had allowed 5 test submissions per team. We received more than 115 submissions in the validation and 65 plus submissions in the test phase. Ensembles were not allowed this year, same as the last year, and we plan to continue doing so. We also provide an extra phase for submissions which violate the challenge rules. Let's announce the winners of this year's challenge. Congrats to Team MIA, which is a joint collaboration between Penang, Jinan University and Central University of Finance and Economics in Beijing. They achieved 70.67% test accuracy, improving the state of the art by a whopping 28%. Congrats to Team Sunlance, which is a joint collaboration between Penang, Peking University and Central University of Science and Technology, Beijing. They achieved accuracy of 65.86% on the test set. Here are the test accuracies of the top 4 teams of 2021 challenge, compared to 2020 winners and the baseline. We see that only a gap of 13% now remains with respect to the human score. Next, let's briefly check out Team MIA's and Sunlance approach. Team MIA pre-trained a T5-3B NLP model from Hugging Face on a dataset of nearly 9 million images. The pre-training data was collected in a similar fashion as the text-aware pre-training work that recently came out. They used improved object features from the WinVL book and collected scene text from using Microsoft OCR. The pre-trained model was fine-tuned only on TextVQA datasets. Team Sunlance improved the image text matching pre-training task of the text-aware pre-training work. In that task, instead of using text subsequences from other images as negatives, they used parts of characters of visual tokens. Here are references to the work that I mentioned in the last 2 slides. Let's dive into some analysis of the top 4 submissions this year and see how their results compare with each other in different scenarios. This plot shows the accuracy of models when answer exists in the OCR tokens of the image. We find that Team MIA's entry performed best with 15% gains over the 2020 winners. It is also noteworthy that Microsoft's entry is an outlier and also has a very good capability of using these OCR tokens. Multiword answers require models to piece together correct OCR tokens from the available vocabulary. In this scenario, we see 15% improvement by Team MIA over the 2020 runner-up submission. However, there is still a good scope of improvement in this category. We see that MIA does a really good job over previous approaches and improves the accuracy more than 23% when answers are previously seen by the model during training.
Even more impressively, the accuracy on unseen answers has been increased from 34 to more than 64% by MIA. Here are some key takeaways from this presentation. Pre-training with image text matching contrastive objectives on huge data leads to significant gains. Developing hard negatives for such objectives also improves performance. There's a scope of improvement in multi-word answers. Using a pre-trained NLP models as a base also helps. Lastly, improved object and scene text features also lead to some gains. Before finishing, I would like to share the release of this new benchmark for text recognition and arbitrary shaped scene text called TextOCR from my colleagues at Facebook Research. If you are interested, feel free to drop by at their poster session on Wednesday at CVPR. Thank you for listening to this talk.